All right, welcome everyone to today's explainer. Get ready because we're about to embark on a seriously mind-expanding journey into the mathematical scaffolding of the universe itself. Today, we're demystifying conformal field theory, or CFT for short. If you've ever found yourself wondering how the deepest foundations of physics connect, from the absolute highest energies down to the lowest, well, you're in exactly the right place. Okay, real quick, here's our syllabus for today. We'll start with a welcome to conformal field theory, then dive into the symmetries of spacetime, renormalization and fixed points, the magic of two dimensions, and finally wrap things up with the state operator map. Section 1. Welcome to conformal field theory. There's this absolutely brilliant quote from the source material that I just love. It says, "Conformal field theories are the mother of all theories as well as, in some sense, the daughter of all theories." Just think about that for a second. Within the massive, totally infinite landscape of all possible quantum field theories, CFTs aren't just random, arbitrary points on the map. No, they're the alpha and the omega. They're the fixed points where physical reality originates and where it ultimately terminates. But okay, before we get too deep into why that is, we need to nail down what the word conformal actually means. So, the crucial point is this. A conformal transformation is one that preserves the metric of space-time, but, and this is a big but, only up to a local scale factor. Mathematically speaking, the new metric is just the old metric multiplied by a factor, which we usually write as e to the power of 2 phi. But what does that mean intuitively? Well, it means these transformations perfectly preserve angles, but they don't necessarily preserve distances. Imagine you have a piece of graph paper, and you stretch it unevenly. If you do it in such a way that the grid lines still cross at exactly 90 degrees everywhere, even though the squares themselves are getting larger or smaller, that right there is the essence of conformal symmetry. Moving right along, Section 2, the symmetries of spacetime. Now, if we're working in a spacetime with more than two dimensions, like say our very own four-dimensional universe, the rules of conformal transformations are strictly governed by just four specific generators. You're definitely already familiar with the first two. We have translations, which is just moving from one point to another, and rotations, spinning around an axis. Pretty standard. The third is dilatation, which is simply scaling things up or down uniformly. But the fourth one, that's a bit more exotic. It's called the special conformal transformation, and it's essentially an inversion followed by a translation followed by another inversion. And there's a formal theorem that beautifully grounds our physical intuition here in rigorous math. It states that absolutely every conformal transformation acting on a connected subset of Minkowski space with more than two dimensions is simply a composition of these four generators. That's literally it. Translation, rotation, dilatation, and special conformal transformations. They are the fundamental base-level building blocks of this entire symmetry. Section 3, renormalization and fixed points. So, I want to pose a question to you all. Let's play a game. Imagine you're a lowbrow, effective field theorist. You just like to work in flat, everyday space, trying to figure out how standard particles interact at low energies. Why on earth should you care about changing the metric or abstract scale invariance? What's in it for you? Well, here's the aha moment. In quantum field theory, as we change the energy scale we're looking at, the theory itself actually changes. We call this the Wilsonian renormalization group, or RG flow. I like to think of it like a river flowing down a mountain. The only mathematically rigorous way we know how to define a quantum field theory all the way up to the highest possible energies, what we call the ultraviolet or UV, is to start at a fixed point. And guess what those UV fixed points are? They're conformal field theories. That's our mother theory. Then you perturb that theory. It flows down the energy river, and eventually at low energies, the infrared or IR, it often ends up pooling at another fixed point. And that daughter theory? Also a conformal field theory. So, CFTs are the ultimate signposts. The entire massive space of all quantum field theories is defined by the RG flows that connect these magnificent conformal fixed points. And because these CFT fixed points possess such immense, robust symmetry, they are incredibly constrained. Let's take the two-point correlation function, for example. This basically tells you the probability amplitude of a particle propagating from a point x1 over to x2. In a normal run-of-the-mill theory, this could be a really messy, complicated function. But in a CFT, the combination of dilation and special conformal transformations literally forces this function into an exact, elegant mathematical form. It scales perfectly with the distance raised to the power of 2 delta, where delta is the scaling dimension of the field. The symmetry entirely, 100%, dictates the physics.
Section 4. The Magic of Two Dimensions.
Okay, so remember just a few minutes ago how I said that in higher dimensions we're strictly limited to those 4 generators? Well, actually, scratch that if you drop down to 2D. In 2 dimensions, the number of conformal generators absolutely explodes to infinity. It's wild. Because of the way light cone coordinates work in 2D Minkowski space, you can redefine your left-moving coordinates and your right-moving coordinates by completely independent, completely arbitrary holomorphic functions. This creates a massive, infinite-dimensional local algebra known as the Witt algebra. Looking at the math, a smooth map in 1 plus 1 dimensional Minkowski space is conformal if it hits these specific derivative constraints. And it basically boils down to pairs of smooth functions. Any arbitrary reparameterization of the complex plane that satisfies the Cauchy-Riemann equations, meaning it's a holomorphic function mapping z to some function f of z, is a completely valid conformal transformation locally. And since there are infinitely many such functions, you have an infinite number of symmetries to play with. This gives physicists an unbelievable, almost magical amount of power to solve these 2D theories exactly. Which brings us to our final section, Section 5, the state operator map. The state operator correspondence. This is a convergent, one-to-one map between states in the Hilbert space evaluated on a sphere and local operators inserted at a point in flat Euclidean space. I know, it sounds a little abstract, but it's really a profound dictionary that lets us translate between 2 completely different ways of looking at quantum mechanics. Here is the gorgeous 3-step logic behind how this works. First, we take our theory and place it on a space that looks like a sphere multiplied by time. Second, we apply a really clever coordinate transformation, a conformal mapping that flattens that cylinder out into a flat plane. But here's the absolute trick of it. Time evolution on the cylinder mathematically transforms into radial scaling on the flat plane. So moving forward in time is exactly the same as zooming out from the origin. And third, well, if moving forward in time is zooming out, then going backward into the past means shrinking the radius closer and closer to the origin. If you take an entire quantum state on a sphere and shrink it down all the way to a radius of 0, it becomes literally indistinguishable from a single local operator sitting right at the origin of space. We have successfully, magically swapped a quantum state for a geometric operator. All right, as we wrap up today's explainer, I want to leave you with a bit of a provocative thought. We've seen that conformal field theories are the mother and daughter of all quantum theories, governing the flows of high and low energies. We've seen how they unlock infinite mathematical symmetries in 2 dimensions and how they seamlessly map the flow of time right onto the geometry of space. So, if these profound infinite symmetries truly define the starting and ending points of all physics, how deeply did they constrain the actual physical fabric of our universe? Think on that as you review today's notes. Until next time, keep questioning the map of the universe.